All right, so I'm trying something new. You're going to see a message up at the top that says that I'm using webcam-free video recording. What that means is I'm actually using my phone as a document camera because I think it will actually be clearer than my crappy document camera. I have this like precarious setup of books at an angle because I write with my paper at an angle and I didn't want you guys to have to look at it at an angle. None of that matters. What does matter is that in class we did not work problem number 16 from section, oh goodness, what section is this? Um, 10.5, rotational kinetic energy and moment of inertia. And so I'm going to work that problem really quick. It says a typical car engine delivers 2 megajoules of energy per kilometer on average. A new car is designed to use the energy stored in a flywheel. If the flywheel has a mass of 100 kilograms and a maximum speed of 400 revolutions per second, find the radius required to give the car a cruising range of 300 kilometers. Treat the flywheel as a uniform cylinder. So this actual problem isn't very hard, but it's kind of a pain in the butt because there are a whole bunch of conversions. None of them are very hard, you just have to do all of them, which is dumb. Um, so like it tells us that we have 2 megajoules of energy. Mega is times 10 to the 6th. So E total equals 2 times 10 to the 6th joules, but that's not actually an energy. It's an energy per distance, and it's per kilometer. I forgot how to write K's for a second. So that's not actually an energy until we multiply it times a distance to get rid of this. Energy per distance isn't really a thing. That's not even like power because that's energy per time. So this isn't really anything. But if we multiply it times the fact that we want to go a total of 300 kilometers, we actually don't have to convert that since this is in kilometers and this is in kilometers. The kilometers will cancel out. 2 times 3 is 6, and we're going to add 2 more zeros. So we get 6 times 10 to the 8th joules of energy, which is quite a lot. So we're trying to figure out what radius we need to be able to generate that much energy, basically. So we're going to use the kinetic energy formula. And since we're dealing with something that's rotating, it is 1/2 I omega squared instead of 1/2 mv squared. And we're given omega. I knew there were more conversions, but why do I keep saying It's in revolutions per second. That's not what we want. We want radians per second. But that's a pretty easy conversion. To go from revolutions to radians, you just multiply by 2 pi. So you get something around, I think I rounded, but you get something around 2,513 rads per second. All right, great. So we have omega, but we need I. I equals question mark. It says to treat the flywheel as a uniform cylinder. So I for a cylinder is one of the ones you should probably know, although I think the AP would even give you that, but it's one of the easy ones. Remember that a point mass or a hoop is going to just be I equals mr squared. For a uniform disc or cylinder, I is going to be 1/2 mr squared. So if we plug that back in up here, we get 1/2 times 1/2 mr squared omega squared equals 1/4 mr squared omega squared is equal to kinetic energy, because that's what this whole thing was over here, kinetic energy, kinetic energy. Now we have everything but radius, so we just have to solve for radius. So 1/4, oh, and they gave us the mass. It was 100 kilograms. I never wrote that down. 1/4, I like when I say one thing and write another. You guys have watched me do that in class. 1/4 times 100 times r squared times 2513 squared equals 6 times 10 to the 8th. And so you're just going to, you will multiply 6 times 10 to the 8 by 4, and so you'll have 24 times 10 to the 8th, but then you're going to divide that by 100, divide that by whatever this is squared. And so you're going to end up with r squared equals 3.8. And that means that r equals 1.95 meters. Some of you may notice that the equation for moment of inertia or rotational inertia, I need to start using the AP term. Oh, you can't see my answer. Boop. 1.95 meters. It's a pretty big wheel, but if it's generating enough energy for a whole car, I suppose that's reasonable. Some of you will notice that the equation sheet has this m and this r as capital letters. That's just to denote that it's the whole radius or it's the whole axis of rotation and the whole mass, which in some cases is different than the radius of the object. Like some of the examples we looked at in class, it's really not a big deal. I wrote them as lowercase here because it just doesn't matter. All right, let's see if this recorded decently.